Hello everyone, and welcome to my channel. This is an educational channel, and we look at theories of everything and other all-encompassing theories that could benefit your life if you knew about them, but they've been suppressed. And today is our 456th video that we've done on Dewey B. Larson and his reciprocal system of theory. Mr. Larson proposed his two fundamental postulates in 1959, declaring his reciprocal system, or otherwise known as his universe of motion. And then over the next years, he derived a theoretical universe based on those postulates through a process of deduction, if this then that approach. And his theoretical universe would have been, or was, what the universe would look like if his postulates were correct. And then he compared his theoretical universe with the empirical universe of the legacy scientists that they had measured in their laboratories and compiled in their scientific tables. We're looking at one of Larson's books today called Basic Properties of Matter, that is on chemistry primarily, and he looks at some of the basic properties that atoms and molecules have, such as the interatomic distance, the compressibility, the specific heat, and then compares their tallies to his derived equations, and then plugging in all the various elements and compounds to his equations, and then kind of explaining various discrepancies and various similarities between these two sets of numbers, in some cases more than two sets of numbers. Okay, so Larson's two postulates. First postulate: the universe is composed entirely of one component, motion, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. And then the second postulate is less important and more just kind of matter of fact and obvious, although I think it's not correct, but it's basically the universe conforms to the relations of ordinary commutative mathematics. Its primary magnitudes are absolute and its geometry is Euclidean. Basically, the second postulate just says that, math works and geometry works, and we as scientists use these things in order to, logic works, that we use these things to, determine how things operate, and the universe also uses those things. So, now, he says the geometry of the universe is Euclidean. Some of his associates and followers, like me, don't believe that that is the geometry of the universe, or that the geometry of the universe, that is part of the geometry of the universe, but there are other aspects to that are more inclusive. The idea that Dr. Bruce Perret had was that the universe is made out, conforms to projective geometry, of which Euclidean geometry is a subset. So that's why I think that Larson's second postulate needs revising, but in general, the general idea behind it is correct. But the first postulate is where the revolutionary changes are being made, and this first postulate boils down to basically 4 assumptions. The universe is made out of motion. motion is the relationship between space and time, um, a reciprocal relationship between space and time. The universe comes in motion, space, time. Motion, space, and time come in 3 dimensions, and motion, space, and time come in discrete units. And when Larson says that the universe is made out of motion, he's referring to what he calls scalar motion. This is a more generalized kind of motion. It is a motion that has a magnitude but has no specific direction. Normally, when you think of motion, you're thinking of something like velocity. The bike is moving 10 miles an hour north. You give a direction of that motion. But a scalar motion is a motion that has no specific direction. You can imagine the surface of a balloon that you put a bunch of dots on, and you blow up the balloon. All of the dots will be moving away from each other, but in no specific direction. Every dot will be moving in every direction. Every dot will be moving away from every other dot, but you won't be able to impute any type of direction to that motion. And the same is true when you suck in the balloon. When you suck in the balloon and the balloon contracts, all of the dots will be moving toward each other, but they won't be moving in any specific direction. And you can abstract that balloon or find a reference point. You can say, okay, this particular dot, I am deciding that it is motionless because I'm making, it's my reference point. I'm making measurements from this. So if you decide to do that and you hold one of the dots motionless, then you can start to determine directions. And in particular, what you will notice is that it will appear as if there is a force field surrounding that reference dot, and that all of the other dots will appear to be attracted to that dot. They'll all be moving toward that one dot. That is what Larson calls an as-if force, or an apparent force. That's not true. It's the result of you assigning a reference system, not the result of the motion itself. The motion itself has no direction. But when you hold one of the dots still, then you can start measuring the direction. So the reference point is what is responsible for the directions, not the motion itself. The motion itself is scalar and has no specific direction. The force is as if or apparent only. When we have that outward motion of the balloon, Larson refers to that as the progression. And when we have the inward motion, Larson refers to that as gravitation. Gravitation is, again, an as-if force. Its directions are not real. The inward force of gravitation, what makes something gravitate, is the same thing as what makes it matter in general. Matter, the whole notion of matter is that it is basically on this inward contracting balloon. All atoms are being attracted to all other atoms, and all matter is being attracted to all other matter. They are all moving toward each other, and they are moving under their own motion, not as a result of being involved in a force field. They're moving under their own motion, and their motion is the matter itself. And so the question is, how does one go from that outward motion of the balloon, the progression, to this inward motion of the balloon, matter? And that is, first, the motion has to be reversed, and it has to be really reversed in 3 separate dimensions, 3 scalar dimensions. Like Larson says, the universe is 3-dimensional. And so if you roll back that outward motion in 1 dimension, it doesn't really do anything. It still appears as if the motion is outward on the balloon at the speed of light. And that's because if you have 3 dimensions of, it's because of the discrete unit postulate. That 4th prong of the first postulate, the space, time, and motion are all in discrete units. And that means that if you have to have a full unit of space, time, or motion in order to have anything. If you don't have a full unit, you have nothing. And if you have 1 unit of space in 1 unit of time, that is 1 unit of speed. Space over time is speed. The bike is moving 10 miles per hour. 10 miles of space in 1 hour of time. That is a reciprocal relationship between space and time. But 1 unit of space in 1 unit of time is also known as the speed of light. Larson calls that unit speed. 1 over 1 equals 1. Unit speed, and that is the speed of the progression. The progression moves outward at unit speed, or the speed of light. And but the math is that 1 to the 3rd power equals 1 to the 2nd power equals 1 to the 1st power. So when you have unit speed, or 1, if it's going in 3 dimensions, it looks the same as if it's going in 2 dimensions. So when you roll back that 3rd dimension of motion, the thing that you that is the result of that motion, which is the photon. The photon is the rolling back of that 1st dimension of motion. That is still apparently moving outward at the speed of light in all directions. And then when you roll that back, that first thing, that's a vibratory motion, a wave-like motion. You can basically think of the wave-like motion on the surface of that expanding balloon, and that's basically your photon. And then you take that photon and you rotate that back, and that is what you call a massless particle, like an electron or a positron. And that then is rolled back in 2 dimensions. But since 1 to the 3rd power equals 1 to the 2nd power equals 1 to the 1st power, it still appears to be going outward at the speed of light in all directions. That's a massless particle. We observe that also as receding at the speed of light. So it's not till you roll it back that 3rd time, or really that 2 of those particles combine together. So you have 2 photons at the core of this double motion, that you get a particle that has mass. And then once a particle has mass, then it stops. And then you really have to rotate it again to get it to roll back into, I'm not completely clear on that you rotate it back again, but you have to roll it back 3 times before you get matter, and then you have the contracting balloon rather than the expanding balloon. Now, when Larson notates that matter is a 3-number combination, first is a 1-dimensional rotation, first is a 2-dimensional rotation. That's your A number. Your B number is a secondary 2-dimensional rotation. A and B alternate. So as you build up in the periodic table, you go, at first the first element is helium 210, and then the second element in this that's the C number, is a one-dimensional rotation. So you have a 3-number set in Larson's periodic table. Helium is 210. You have to have a full motion in each one of those 2 dimensions because, again, with this progression of the natural reference system, that is always there. So you always have to take that into account. So you have to have a full motion to nullify that. And that is then why you need to have helium as 210 to be the first, really the first stable element. Hydrogen, the first, the mass 2 isotope of hydrogen called deuterium is not stable. The mass 1 isotope of hydrogen is not considered to be a full atom. It is what Larson calls an intermediate particle, and it is the combination of 2 of these other particles. But so helium is really the first atom on Larson's table, and then those alternate 210. So the next one is 220. That would be neon. And then the next one would be 320, argon. So the noble gas series is building up on these two-dimensional rotations, and the gaps are filled in with this third number, which is the one-dimensional electric rotation. So for example, if you have 211, that is lithium, number 3. 212 is beryllium, number 4. 213 is boron, number 5. 214 is carbon, number 6. But carbon, just as probable, it could be that carbon would be 2-4 because it's equally the same distance from helium as it is from neon. So it could, by probability, and probability is what governs the universe conforms to the relations of ordinary commutative mathematics. That's the second postulate. So probability determines these things. So that's kind of how you get matter out of this whole thing. And again, the universe is made out of space, out of motion. Motion is the relationship between space and time. So all basically motion is a fraction with space or time as the numerator and time or space as the denominator, just like speed is space over time. And it's a reciprocal relationship. You double the speed and you say the car is now going 20 miles an hour instead of 10 miles an hour. Or you can say the car is now moving 10 miles per half hour. You can either double the space or you can divide the time. So that is a reciprocal relationship in speed. But Larson extrapolates that to everything. All forms of scientific phenomena are kinds of motion. Matter is a kind of motion. Energy is a kind of motion. Force is a kind of motion. Pressure is a kind of motion. Gravitation is a kind of motion. Electric charge is a kind of motion. And they all have time and space coordinates, or exponents in their fraction. Matter is time to the third over space to the third. Pressure is time over space to the fourth, and so on and so forth. And then you have this other aspect of the three-dimensionality is the coordinate space and coordinate time. This is when you abstract really that you have a gravitationally bound system. When you have this gravity of this contracting balloon, then you start getting vectorial motions where you can determine the directions. And that is coordinate space. When you have coordinate space, you can say X, Y, Z coordinates. And that is a three-dimensional picture in a still frame. This is a three-dimensional backward. This is the normal universe that we're accustomed to. 3 dimensions of space unfolding in time. Time is still scalar. Time is getting later and later and later and later, but in no specific direction. Now, and this is in our gravitational side of the universe. But there is a reciprocal part of the universe where that same thing occurs in time instead of space. So you have 3 dimensions of time in a still frame, and you have clock space. Space is always getting later or further and further and further apart, but in no specific direction, like on the surface of an expanding balloon. Larson calls that the cosmic sector. That is the sector that is moving faster than unit speed, or the speed of light. So there's 2 sectors here in this universe, a cosmic sector and a material sector. The material sector is what we're accustomed to, but there is this cosmic sector with space and time interchanged. It's a reciprocal of our material sector, where you have 3 dimensions of time moving through space, as opposed to 3 dimensions of space moving through time. And then you have subregions of both of those material and cosmic sectors, where the discrete unit postulate takes over again. In the material sector, if you have atoms and molecules that are interacting in less than 1 unit of space, when they approach 1 unit of space, they can't get any closer, because you can't get less than 1 unit of space. So instead, you move in time, but you move outward in time, which is the equivalent of inward in space. Larson calls that the time region. All motion is in time, because it's not in space, because you have to have a full unit. And this is what it would be equivalent to less than 1 unit of space. So it occurs in time. And again, you have to invert the roles when you cross that boundary. And now the progression is moving inward in equivalent space, and gravity is moving outward in equivalent space. And this is the realm of atoms, molecules in the solid state. And the same is true over in the cosmic sector, except it's called the space region instead of the time region, and it is inside 1 unit of time. Okay, now let's read some of Larson's writing here from his book on temperature relations. Now, this is interesting. This is chapter 7, and we started this yesterday, but we'll get into the temperature relations. What you have to keep in mind, the main point here is that, unlike legacy science that believes that temperature is the result of an aggregate of millions and trillions of different atoms, in Larson's world, his universe of motion, temperature is indigenous to the atom or the molecule. He calls it the thermal unit. So every atom or molecule has he calls it a thermal group or thermal unit, has its own temperature. Okay. Scalar motion in 1 dimension, when seen in the context of a stationary spatial reference system, has many properties in common with vectorial motion. This no doubt accounts for the failure of previous investigators to recognize its existence. But when motion extends into more than 1 dimension, there are major differences in the way these types of motion present themselves or do not present themselves to observation. Any number of separate vectorial motions of a point can be combined into a single resultant, and the position of the point at any specified time can be represented in a spatial system of reference. This is a necessary consequence of the fact that vectorial motion is motion relative to that system of reference. But scalar motions cannot be combined vectorially. The resultant of scalar motion in more than 1 dimension is a scalar sum. and it cannot be identified with any one point in spatial coordinates. Such motion is therefore incapable of representation in a spatial reference system of the conventional type. Now, when Larson is referring to the spatial reference system, he's really talking about coordinate space and clock time. This still background, and we're progressing. Things are unfolding through time. Time is getting later and later and later. That's the spatial reference system, or the stationary reference system. This is the normal reference system that science goes by. But when we have this progression, the scalar reference system, Larson refers to that as moving outward at the speed of light in all directions. That is the 0 point of Larson's universe. This is the ether, or the origin, or the null point of Larson's universe. It's the fulcrum, meaning that half the universe is moving slower than that, half is moving faster. And this is the moving reference system, the natural reference system that nature actually conforms to. And he's basically saying that we need to conform to this system also, or else we're going to get our science all wrong and our measurements all wrong. We have to, conform to this system also, or else we're not going to be able to actually get the full picture of what's going on. We can use this spatial reference system, and we can use the temporal reference system in certain instances, but we can't. But we have to recognize, like, the full picture, that when we're using the spatial reference system, it's an abstraction, and it's for convenience. It's not for reality. It's for, making measurements, but this is not really what's going on. What's really going on is the progression of the natural reference system, which is omnipresent and eternal. It occurs in all locations at all times. Okay. This is a necessary consequence of the fact that vectorial motion is motion relative to that system of reference. But scalar motions cannot be combined vectorially. And the result is a scalar sum. Okay? It does not follow, however, that inability to represent this motion within the context of a severely limited kind of reference system, such as the spatial reference system, that we are accustomed to use, means that such a motion is non-existent. To be sure, our direct perception of physical events is limited to those that can be represented in this type of a reference system. But nature is not under any obligation to stay within the perceptive capabilities of the human race. As pointed out in Chapter 3, Volume 1, Nothing But Motion, which I went over 8 months ago or something on this channel, where the subject of reference systems was discussed at length. There are many aspects of physical existence, that is, many motions, combinations of motions, or relations between motions, that cannot be represented in any single reference system. This is not in itself a new or unorthodox conclusion. Most modern physicists, including all of the leading theorists, have realized that they cannot accommodate all of present-day physical knowledge within the limitations of fixed spatial reference systems. But their response has been the drastic step of cutting loose from physical reality and building their fundamental theories in a shadow realm, where they are free from the constraints of the real world. Heisenberg states their position explicitly, quote, "The idea of an objective real world whose smallest parts exist objectively in the same sense as stones and trees exist independently of whether or not we observe them is impossible," he says. In the strange half-world of modern physical theory, the only realities are mathematical symbols. Even the atom itself is, quote, "in a way only a symbol," Heisenberg tells us. Nor is it required that symbols be logically related or understandable. Nature, these front-rank theorists contend, is inherently ambiguous and subject to uncertainties of a fundamental and inseparable nature. Quote, "The world is not intrinsically reasonable or understandable," says Percival Bridgman. "It acquires these properties in ever-increasing degree as we ascend from the realm of the very little to the realm of everyday things." End quote. What the reciprocal system of theory has done in this area is to show that once the true status of the physical universe as a universe of motion is recognized and the properties of space and time are defined accordingly, there is no need for the retreat from reality or from the attempt to blame nature for the prevailing inability to understand basic relations. The existence of phenomena not capable of representation in a spatial reference system is a fact that we must come to terms with. But the contribution of the reciprocal system has been to show that the phenomena outside the scope of the conventional spatial reference systems can be described and evaluated in terms of the same real entities that exist within the reference system. The scalar sum of the magnitudes of motion in different dimensions, the quality we will now use in analyzing the temperature relations, is an item of this nature. It is just as real as any other physical quantity, and its components, the motions in the individual dimensions, are motions of the same nature as those one-dimensional scalar motions that are capable of representation in the spatial reference systems, even though the scalar unit cannot be so represented in any manner accessible to our direct perception. Okay, we're going to stop there for today. I know that was fairly short reading, but there was a lot there, and I think this is like the crux of the matter, and why this is so important to me is, the scientists have jettisoned the idea of reality because they figured they couldn't figure out reality, so they just assumed that it can't be figured out. This is like this principle of impotence. There's no other way to do it. We have to basically get rid of the concept of reality and assume that these atoms and molecules participate in this kind of quasi-shadow world of somewhat reality, of symbolism and charm and these other qualities that it assigns to their quarks. But in reality, it's just that we have to look at it in a more reasonable way. Okay, thanks for tuning in.